The title of this note is Piecewise Functions, and the outcome is to determine if a piecewise function is continuous. So a function is continuous if every piece connects to the next. If you imagine tracing the function with your pencil, you would not have to pick up your pencil to trace the entire function if it's continuous. So how do you check for continuity? You're going to substitute the x value of what I'm going to call the breakpoint. That's where the two branches, the domain switches. You're going to substitute the x value into both branches, and you're checking to see if the output is the same. If y values are the same, then the function is continuous. So let's look at an example of this. Here we have a function. It has two breakpoints. We have a rule to the left of 8, we have a rule at 8, and we have a rule to the right of 8. So the first break is between these two branches here. So we're going to set them equal to each other. And they break at 8. So now we're going to substitute 8 into x. 8 to the 1/3 power. The 1/3 power is the same thing as the cube root of 8. So it means what to the 3rd power gives you 8. And that's positive 2. Since they're equal, it's continuous at that breakpoint. We need to look at the other side. So same thing. Set those two branches equal to each other. They break on the other side of 8. So we're substituting 8 in for x and we're solving. Those are also the same. So this piecewise function is continuous. If we were to graph all three pieces, they would all connect. We would not have to pick up our pencil to go from the first piece to the second piece to the third piece. Because it has 3 branches, we had to check 2 places. So in the last one, you saw a function, and you were asked to see if it is continuous. Another type of problem you're going to see is you're going to have a function, and you're going to be asked to force it to be continuous. So it's going to work much the same way. You're going to set those 2 branches equal to each other. You're going to substitute the breakpoint, and then you're going to solve. So let's look at an example. All right, so here's an example. X is the variable. So you'll notice there's these other letters A and B. A and B are unknown numbers that you're going to solve for. So the question is, what do A and B have to be so that this function is continuous? It needs to be continuous at 0, and it needs to be continuous at 2. So just like on the last problem, we're going to have to do this twice. So make the function continuous at 0. We're going to set the 0 affects the first branch and the second branch. That's 0 is where those first 2 branches meet. So we're going to set those 2 branches equal to each other. And we need those 2 branches to equal each other at 0. That's where we need them to connect. So we're going to substitute 0 in for x. A and B are what we're trying to figure out. So now solving, a times 0 is just 0. So that just leaves behind 2b. 0 squared is 0. Now you'll notice I have 2 variables. So if I have 2 variables, it's a system. I'm going to need 2 equations. So right now, all I know, I can keep going, I can divide by 3. Right now, all I know is that B has to equal A. So whatever I get for A, or whatever I get for B, they're going to be the same answer. So we have to do this twice, because we have 2 variables to solve for. We're solving for A and B. Okay, so now we're going to check at 2. 2 is where the second and third branches meet. In order for this to be continuous, we need them to meet, which means we need them to be equal at the input 2. So we're setting those 2 branches together, and then we're going to substitute 2 in for x. And simplifying as much as possible. So I have 4 plus 3a minus b equals 1, and I'm going to subtract 4. So 3a minus b equals negative 3. So now I have two equations, which is how many equations I need to solve for two variables. So I have a system here. You can do substitution, elimination, or you could use your Gaussian elimination if you wanted to. This one's actually a pretty easy one to do with just substitution. Since b and a are the same number, this b right here, you can replace it with an a. Because this fact over here is that b and a are the same. So 3a minus a is 2a. So a is negative 3 halves. And since a and b are the same, b is also negative 3 halves. Lastly, we're going to talk about absolute value functions. Absolute value functions, they're coming up right now because they can be rewritten as piecewise functions. That's actually going to be a very helpful skill when you take calculus. A lot of time calculus problems will present absolute value functions, and the only way they can be analyzed is by turning them into piecewise functions. So to take an absolute value into terms, you have three steps. First, you need to identify the vertex of the absolute value function. Then you're going to write the piece to the right, and you're going to treat the absolute value just like parentheses. Then you're going to write the piece to the left of the vertex, and anything that was in that absolute value in those kind of parentheses, you're going to take the opposite of each of those values. So let's look at an example. Okay, here's a function, absolute value function. I can tell that this absolute value function is opening down because of the negative in front of the absolute value. I can also tell the vertex of this function. Absolute value bars act like parentheses. Anything in parentheses changes sign. So the x-coordinate is positive 2, and the y-coordinate is positive 3. That plus 3 is not in any sort of parentheses or bars or brackets. This is the vertex. So if we wanted to graph this, we would go to 2, 3, and we draw an absolute value function. That's like a negative 1. So it would have a slope of negative 1, and then on the other side it would have a slope of positive 1. So there's a sketch of that absolute value function. So we're going to write it as a piecewise. We're going to have a piece to the right of the vertex, and we're going to have a piece to the left of the vertex. So to the right of the vertex, that function is going to be almost like the original. The original has the absolute value bars. We're just going to treat the absolute value bars like parentheses. And then we're going to simplify. I can distribute that negative 1. Once it's distributed, we can drop the parentheses, and we can combine the like terms. So the equation of this piece in red is negative x plus 5. To find the piece to the left, we're going to go back to the original function, treat it like parentheses, but we're going to do the opposite. We're really just concerned with what's in those parentheses. It's a positive x, so you're going to think of it like a negative x, and then you have a negative 2, so it becomes a positive 2. Nothing else changes. And that's how it has two answers. Both the positive and the negative have the same absolute value. So the positive is to the right of the vertex, the negative is to the left. Now it's just like the other one. Go ahead and distribute your negative, and then simplify. So the equation of this piece is x plus 1. So the last thing we want to do is we want to write that as a piecewise function. So we're going to write f of x equals, and then write each piece. It doesn't really matter which piece you write on the top, which piece you write on the bottom. Just remember that you need your domain restrictions. So this red piece, negative x plus 5, that's to the right of the vertex, so when x is greater than 2. And then the piece to the left of the vertex is when x is less than 2. And then which rule should you use it to? Well, you can pick. it can follow either the green rule or the red rule. So one of those gets the or equal to sign. Doesn't matter which one as long as it's only one. So this here in black, that is a piecewise function that matches that absolute value function. This is the end of our notes.